Hello friends. Welcome to my YouTube channel Chemical Adda. Please watch this video till the end to learn about the vapor compression refrigeration cycle. In this video, we will discuss about what is the vapor compression refrigeration cycle? What is the working principle of it? What are the components? How it works? What is the coefficient of performance? What are the applications? And what are the advantages and disadvantages of vapor compression refrigeration system? First, we will begin by studying about vapor compression refrigeration system. So, vapor compression refrigeration is the most common refrigeration cycle for building and car air conditioning. Hence, there are many different refrigeration cycles, but the vapor compression refrigeration system is the most commonly used method for the air conditioning automobiles and buildings. The vapor compression refrigeration cycle is also called the vapor compression cycle. Then the vapor compression cycle occurs within a closed system. In this system, the working fluid that is refrigerant is a vapor, which readily undergoes evaporation and condensation, alternately changing between vapor and liquid phases. So in this system, the refrigerant absorbs heat Q2 from the cold space, which is to be cooled or refrigerated, and this cold space acts as a source of latent heat, and thus refrigerant gets converted to vapor from liquid. Then this refrigerant vapor rejects heat Q1 to the cooling water in the condenser and gets converted from vapor to liquid. Hence, vapor compression refrigeration system is also called a latent heat pump, since it pumps latent heat from the cold space and delivers it to the cooling water. Therefore, many industrial plants use huge vapor compression refrigeration systems, including oil refineries, petrochemical and chemical processing plants, and natural gas processing plants. Now let's understand the working principle of the vapor compression refrigeration cycle. So, the vapor compression cycle in the refrigeration system operates on the principles of the reverse Rankine cycle. Now, let's have a look at the components of the vapor compression refrigeration cycle. So, the typical vapor compression system consists of 4 components. The first component is the compressor, where the reversible adiabatic compression, that is, isentropic compression, of the vapor occurs. Then the second component is the condenser, where reversible constant pressure condensation, also known as heat rejection, occurs. Then the third component is the expansion valve, also called a throttle valve. Here, an irreversible adiabatic throttling process or expansion process is carried out. And the fourth component is the evaporator. Here reversible constant pressure evaporation, also known as heat absorption, is carried out. Now, let's discuss this process of vapor compression refrigeration system in detail. The processes that are completed in one cycle are compression, condensation, expansion, and evaporation. So, the first step of the process is reversible adiabatic compression or isentropic compression, which is carried out in compressor. The refrigerant vapor leaving the evaporator is dry and saturated, and it enters the compressor at low temperatures and pressures. Here, in the compressor, isentropic compression or reversible adiabatic compression is carried out to raise the temperature and refrigerant pressure, hence we will get superheated vapor. So to raise pressure and temperature of refrigerant, compressor requires work W or WC, for that electric motor may be used. Hence in the compressor, during the process, entropy is constant, but the pressure, temperature, and enthalpy of the refrigerant are increased. This is represented by the lines 2 to 3, in temperature entropy, that is TS diagram, and pressure enthalpy, that is pH diagram. Then, the next step of the process is carried out in the condenser, which is a heat exchanger. In this step, reversible constant pressure condensation or heat rejection is carried out in the condenser. The superheated vapor, leaving the compressor, enters the condenser, where heat Q1 is extracted from the refrigerant and gets condensed into a liquid at the pressure maintained in the condenser. So, in the condenser, the latent heat of condensation Q1 is extracted from the refrigerant vapor with the help of a cooling medium, such as cooling water. Hence, during the process in the condenser, the vapor is initially cooled to remove superheat. This is represented by the curved line 3 to 3' in the temperature entropy diagram, and then this vapor condensed at constant temperature and pressure and produces saturated liquid. This cooling and condensation process in the condenser is represented by lines 3 to 4 in the temperature entropy, that is TS diagram, and pressure enthalpy, that is pH diagram. Now, the next step of the vapor compression refrigeration cycle is the irreversible adiabatic throttling process or expansion process, which is carried out in the expansion valve or throttling valve. In this step, the liquid refrigerant flows from the condenser to the expansion valve, in which a Joule-Thomson expansion occurs. During the expansion of the refrigerant in the expansion valve, pressure decreases. And as a consequence of this, the temperature decreases at this stage, but the enthalpy does not change. Therefore, the specific enthalpy of refrigerant entering and leaving the expansion valve is equal. But the throttling of liquid refrigerant results in the partial vaporization of the liquid refrigerant, hence we obtain a mixture of liquid and vapor refrigerant. Hence, the refrigerant leaves the throttle valve is a mixture of liquid and vapor, typically in proportions of around 75% liquid and 25% vapor. So in the expansion valve, due to the adiabatic expansion process, the temperature and pressure of refrigerant decreases, and this process of expansion is represented by line 4 to 1 in the TS and pH diagram. Therefore, in the vapor compression cycle, throttling valves play two crucial roles. First, they maintain a pressure differential between low and high pressure sides. The second is that they control the amount of liquid refrigerant entering the evaporator. Now, the last step is reversible constant pressure evaporation, also known as heat absorption, which takes place in the evaporator. So, from the expansion valve, a mixture of liquid and vapor refrigerant enters into the evaporator. In the evaporator, heat Q2 is absorbed from the space that needs to be cooled or refrigerated to produce a cooling or refrigerating effect. So, due to the absorption of heat, the liquid portion of the refrigerant gets evaporated, and we get low pressure saturated vapor, which then enters the compressor to complete the cycle. Hence, in the evaporator, reversible evaporation at constant pressure and temperature takes place. This process results in the conversion of a mixture of liquid and vapor into saturated vapor, which is represented by the line 1 to 2 in the TS and pH diagram. And hence, the saturated vapor refrigerant from the evaporator enters the compressor, and thus the cycle is completed. Now, let's understand what is the coefficient of performance of the vapor compression refrigeration cycle. So, the coefficient of performance of a refrigerator is defined as the ratio of the desired refrigerating effect to the work input or supplied to achieve the effect. But, what is the need to find out the coefficient of performance of vapor compression refrigeration system? Because the performance of a vapor compression refrigeration system is expressed in terms of coefficient of performance, which is also called COP. Hence, to get an idea about the performance of vapor compression refrigeration system, we should know the COP. So to derive the formula, first let us assume H2 is the specific enthalpy of refrigerant leaving the evaporator and entering into the compressor. Then, H3 is the specific enthalpy of refrigerant leaving the compressor and entering into the condenser. Next, H4 is the specific enthalpy of refrigerant leaving the condenser and entering into the expansion valve. Then, H1 is the specific enthalpy of refrigerant leaving the expansion valve and entering into the evaporator. Next, W is the work required for the refrigerating effect per kilogram of refrigerant. Next, Q2 is the heat absorbed from the cold body in the evaporator. And Q1 is the heat rejected to the cooling medium in the condenser. So as we know, the coefficient of performance of a refrigerator is the ratio of the desired refrigerating effect to the work input or supplied to achieve the effect. Therefore, from the definition, we can write COP is equal to the refrigerating effect divided by work input or supply. But in the refrigerator cycle, the refrigerating effect is also known as heat absorbed from the cold body. Hence, the formula for ACOP can be written as COP is equal to the heat absorbed from the cold body divided by work input or supplied. But as we know, in a vapor compression refrigeration system, heat Q2 is absorbed in the evaporator from the space to be cooled or refrigerated. And work W or WC is supplied in the compressor by electric motor. Hence the formula for COP can be written as COP is equal to Q2 divided by W, where W is the work required for the refrigerating effect per kilogram of refrigerant, and Q2 is the heat absorbed from the cold body. Now first let's calculate the Q2 and W. Hence, to find out Q2 and W, we should take the energy balance across the compressor and evaporator. So, across the compressor we can take energy balance as the input energy is equal to the output energy. So, from the diagram we can write H2 plus WC is equal to H3. From this equation, we get WC. WC is equal to H3 minus H2. Hence we get the work required for the refrigerating effect per kilogram of refrigerant as W, which is equal to WC, is equal to H3 minus H2. Similarly, let's take the energy balance across the evaporator. So across the evaporator we can take energy balance as the input energy is equal to output energy. Hence from the diagram, we can write as H1 plus Q2 is equal to H2. From this equation, we get Q2. Hence Q2 is equal to H2 minus H1. Hence we get that heat absorbed from the cold body as Q2 is equal to H2 minus H1. Now, let's put the value of W in Q2 in the COP equation. So as we know, COP is equal to Q2 divided by W. Hence, after putting the value of Q2 and W from equations 2 and 3, we get COP is equal to H2 minus H1 divided by H3 minus H2. But enthalpy of refrigerant during the expansion process in the expansion valve remains constant. Hence, we can write H1 equal to H4. Hence we get COP is equal to H2 minus H4 divided by H3 minus H2. Hence from these two equations, we can calculate the COP of the vapor compression refrigeration system. Now let us understand what are the applications of vapor compression refrigeration system. So the first application is refrigeration. So in refrigerators and freezers, the vapor compression cycle keeps the interior cool by removing heat. The second application is air conditioning. So in air conditioners, the cycle removes heat from indoor air and expels it outside, cooling the indoor environment. And third application is heat pumps. So, in heating applications, the cycle can be reversed to provide space heating by extracting heat from the outside air or ground. Hence, the vapor compression cycle is fundamental to modern refrigeration and air conditioning systems. By cyclically compressing, condensing, expanding, and evaporating a refrigerant, the cycle effectively transfers heat from one place to another, enabling temperature control in various applications. Now let's understand the advantages and disadvantages of vapor compression refrigeration cycle. So first advantage is vapor compression has a higher COP than air refrigeration. So when we compare the COP of air refrigeration system and vapor compression system, the COP of the vapor compression system is significantly higher. Then the next advantage is less power is needed for a given capacity. So, if we compare the vapor compression cycle with the air refrigeration system, less power is required for the same amount of capacity. Then the next advantage is the weight of refrigerant circulated per ton of refrigeration is lower than the weight of air circulated in an air refrigeration system. Now let's look at the disadvantages. So the first disadvantage is the initial investment is high. Next disadvantage is the prevention of the leakage of the refrigerant is a major problem. Hence, one of the most significant challenges is ensuring that the refrigerant does not leak. So let's summarize this video. Vapor compression refrigeration is the most common refrigeration cycle for building and car air conditioning. Next point is, it works on the principles of the reverse Rankine cycle. Next, it has four components: compressor, condenser, expansion valve, and evaporator. Then the processes that are completed in one cycle are compression, condensation, expansion, and evaporation. Then last point is, the COP of vapor compression refrigeration system is COP is equal to H2 minus H1 divided by H3 minus H2. So that's all about the vapor compression refrigeration cycle. So keep watching. In the next video, we will discuss another topic. So, if you like my video, please like, share, and subscribe to my YouTube channel, which is Chemical Adda.